This is a very surprising puzzle that blew my mind when I first saw it. We are told that there are 8 cows grazing in a field, and it takes 10 days to consume all the grass. We are now told that if there were 6 cows, it would take 15 days. That makes sense because you'd expect fewer cows would take longer to eat the same amount of grass. You might have expected it to be about 13 days, but it's a little more, as grass still grows over the days that the cows eat. So, how long would it take 3 cows to consume the field? How long would it take 2 cows? And what about 1 cow? Let's first focus on the case of 3 cows. What does your intuition say? Don't calculate anything, just say what first comes into your head. How long do 3 cows take to eat the field? If your guess was 40 days, this is the answer most people give, but it's wrong. People reason that if 6 cows took 15 days, then 3 cows will take double 15, plus a bit extra to account for grass growth. So 40 days feels about right, but the actual answer is 60 days. It's surprising because that's as much as 4 times 15 days. So what's going on? So let's unpack the maths and see how the calculation comes to the surprise of 60 days. I'm going to assume advanced high school or first year university maths. If you don't follow the math, don't worry. Buckle up, as it is still an interesting ride. This is the formula for the time it takes cows to eat the whole field. Let A be the initial amount of grass. Let N be the number of cows. Let B be the uniform rate at which cows eat grass. Assume each cow has an identical rate. Let C be the uniform rate at which grass grows. Let's now do a quick sanity check to show the formula is correct. As you'll see, faster eating rate B reduces the time T. Faster grass growth rate C increases the time T. Okay, so that all makes sense so far. We can simply rearrange the previous formula like this. Here's the case of 8 cows taking 10 days. Here's when 6 cows take 15 days. And lastly, here's 3 cows taking T days. The puzzle is to calculate T. Multiplying out the brackets and rearranging, we obtain 3 simultaneous linear homogeneous equations. From basic linear algebra, we know that these have non-trivial solutions only if the determinant of the coefficients is 0. We would like to now simplify this to get rid of one of the t's. From linear algebra, we know there are operations that leave the 0 determinant unchanged. We can multiply a copy of the third column by 3 and add it to the second column. This then leaves one isolated t element, which is our aim. We can now simplify the center column by dividing each of its elements by -5. Now that this is fully simplified, we can expand the determinant. To expand, we grab the circled element and multiply it by the determinant of those 2 by 2 elements that are not in that row or column. The next circled element is a 0, so we don't need to cross multiply, as this expanded term is going to be 0 anyway. We circle the next element, which is t. We multiply by the indicated 2 by 2 determinant, and we are done. Notice I circled elements on the bottom row to exploit this simplification of having a 0 present. But you can expand along any row or column and you will get the same final result. The expanded result is easy as it only has one t and the middle term is 0. Rearranging gives 60 days as the time for 3 cows to eat the whole field. So how long would it take 2 cows? So the math is identical to the 3-cow case, except that this circled 3 here becomes 2 as we now have 2 cows. So let's swap out that 3 with a 2 as shown here. It doesn't seem that reducing one coefficient by just such a small amount should make much difference, but prepare to have your mind challenged. Let's take a copy of the third column, double it, and add it to the middle column. This neatly simplified the determinant, giving us a 0 element on the bottom row as before. We divide the elements of the middle column by minus 60 to further simplify, and we get this really easy determinant now. Stepping along the bottom row and cross-multiplying out as before, we get a simple expression for t. Rearranging in terms of t, we see something tricky going on. The fraction is divided by 0, which is not allowed mathematically. Remember that mathematics is a dumb machine that spits out numbers, and it is us humans that need to interpret them. In this case, the interpretation is that the grass grows fast enough to always keep up with the 2 cows. So dare we now ask what happens with 1 cow? How many days? Now don't cheat and do any math, just tell me what your intuition says, and then we'll see what the math says. What's the first thing that comes into your head? Most people, after seeing that 2 cows take eternity, say that 1 cow also takes forever. It's not a bad answer, but if we are going to be very strict, it's not quite right. It's subtle. Let's see what the maths actually says. I'm not going to bore you with the determinants. You can easily follow the process I've shown you yourself. After expanding the determinant and rearranging to get t, we get this. And notice, this isn't eternity as before. So let's calculate it. Start the drum rolling. It takes minus 60 days. Well done if you saw negative time coming. Pretty crazy. We could interpret this as a time-traveling alien cow that goes back in time to get a head start to eat the grass. But that's a bit of a stretch physically. The best interpretation here is that 1 cow is simply not fast enough to eat all the grass, and to do so would require it to increase its rate of consumption. So where did this puzzle come from? Well, I first saw it around 1977 in a university-level textbook that was dated somewhere in the 1930s. I've forgotten which book it was, but I've now done some historical research on it, and incredibly, the problem originally goes all the way back to Isaac Newton. The cow puzzle is in this book called Arithmetica Universalis, published in 1707. It was a compilation of Isaac Newton's actual lecture notes, edited by William Whiston, who became the next Lucasian professor after Newton. Notice it is in Latin. If you were in one of Newton's classes, you'd be lectured to in Latin. The cow puzzle is on page 89, and it is listed as problem 11 here. Problem 11 starts here, indicated with the circle. Boves means oxen, so I've modernized the problem to be with cows instead. Depescant pratum means grazing the field. Tempore means time. He says the oxen consume the field in a time c. Graman uniformiter crescat means the grass grows uniformly. Newton frames the problem differently and gives times the oxen take to eat the grass, and instead asks you how many oxen you would need to achieve those times. So, sneaky, this neatly gets out of the problem of negative time, but Newton unfortunately ends up with fractional cows in the process, or fractional oxen rather. However, Newton avoided numbers that resulted in getting any infinities. Remember, in those days, infinity in math was treated with some suspicion, and so it makes sense that Newton avoided that case when lecturing undergraduate students. Philosophizing over infinities and how to interpret them, I suspect, is something Newton left to talking with colleagues down the pub with a mug of mulled wine. If you understood the concepts and haven't started university yet, you may have a talent for chemical engineering. These types of rate equations are what engineers use today to model chemical production processes. Who would have thought that Newton's mucking around with a curious brain teaser formed the math underpinnings for the modern chemical industry? In this video, I made a deliberate mistake. Did you spot it? The plus sign circled here should really have been a minus sign. Fortunately, in this case, it didn't matter as it was in front of a zero. So here's something to ponder on. What if we allowed time-traveling cows? Can you calculate if one cow went back in time by only 60 days, would it be enough to catch up and eat the field of grass by itself? Let me know what you find out and leave your answers in the comments. Here's another thing to ponder on. What would happen if we stopped assuming uniform growth of grass? What if we assumed exponential growth or other types of curves? Would the negative time issue disappear or would it worsen? Feel free to try it out and leave your answers in the comments.